Okay, it's time to start. Welcome everyone at our first colloquium this year. And following our good tradition, this colloquium will be given by Professor Iwo Białynicki Birula, who will tell us about new role for Spinors.
Thank you. I had a dilemma because I could have started this talk from the end and then you would be surprised how come. So it's better to start from the beginning and to show how this end happened. And at the end you will be in six-dimensional space. So this is in a way a continuation. We were doing various investigations and the subject was interesting, knotted or linked solutions of Maxwell equations. Later it turned out that one can also do this for the Dirac equation. And you will see today that there is a common base for all these knotted solutions of relativistic wave equations. There are many relativistic equations, starting from the sort of trivial Klein-Gordon equation. Then we go further to Weyl equation, which is a relativistic equation for spin 1/2 particles. Then we have photons, which is a relativistic equation for spin 1 particles. Then we come to the Dirac equation, and this turns out to be all part of a general scheme. I love Spinors. This is my favorite motto by Andrzej Trautmann. One is tempted to say that the world around us and life in particular are so rich because nature found it convenient to use among its building blocks entities requiring spinors in their... This sounds like a slight exaggeration. However, it was published. I am not here. Then we have Michael Atiyah, who died recently, great mathematician. No one fully understands spinors. Their algebra is formally understood, but their geometrical significance is mysterious. In some sense, they describe the square root of geometry, and just as understanding the concept of -1 took centuries, the same might be true of spinors. And finally, I have a quotation from Felix Klein, because I would like to stress what was the essence of the so-called Erlangen program by Klein, who decided that various mathematical structures are better understood when we start from transformations from symmetry groups. And in physics, this is especially true. Notice that this use of manifoldness indicates that the translation was done at the very beginning of the century, where the concept of manifold was named manifoldness. Okay, so now we come to the group of transformations. This will be the Poincaré group that will play the essential role because spinors are, after all, relativistic objects. So in the Poincaré group, we distinguish the generators. All transformations of the Poincaré group are generated by the energy, which is the time component of the momentum vector. Then there are generators of translations. We have three-dimensional rotations and three special Lorentz transformations. And these generators can be combined into relativistic objects. We have the four components of the momentum vector and 6 components of the angular momentum. They obey the commutation relations, which are generalization of what we know from non-relativistic physics. nothing special. And now we come to spinors. My knowledge of spinors started when I was a student and I was reading the book by Corson. And this is where I got this notation. Corson introduced the notation, capital letters for the components of spinors. Spinors, as you know, are two-component objects, and of course everybody knows spinors from the wave functions that are of spinor type. The new role here, as you will see, is different. We start from spinors as elements of the representation theory of the Poincaré group. So they have no relation so far to the waves in space-time. And this is what the spinors are like. They have components, and the notation comes from Roger Penrose, who introduced this notation that 0 and 1 are the names of the components. It's hard to tell. I asked Penrose, and he did not remember how come he used this convention. And now it's stuck, and most people use this. Now, this is a tricky space. Namely, we have sort of a metric tensor. However, it is anti-symmetric, so it has nothing to do with our notion of metric tensor, which should measure the length. But this particular anti-symmetric matrix plays the role of the metric tensor because it is invariant under the transformations that spinors undergo. When you form a scalar product of two spinors using this matrix, you find that this scalar product is invariant under the transformations. Now, there are two objects that are very convenient, and they are called spin tensors because in addition to having spinor indices, they also have vector indices. So this is sort of a dual object. It's very simple. It's a combination of Pauli matrices. However, it's very convenient. When you take a product of such, of course, here repeated indices mean always summation, and the object here is sort of an angular momentum because it tells us how spinors behave under the transformations of the Poincaré group. And the dotted spinors, as was written, there are just complex conjugate of the ordinary spinors. Now they form the fundamental representation. Fundamental means that this is the lowest dimension representation. The representation that has one component is sort of trivial. This is the scalar representation, so nothing changes, and spinors do change. Under an infinitesimal transformation here, spinors undergo the transformations, which is also an infinitesimal transformation, and it is precisely this matrix that rotates these spinors when we apply transformations of rotations and Lorentz transformations. Now, something happens which is sort of new here, and nobody used spinors for that purpose. Namely, at this moment, I introduce a function of spinors. Spinors are like numbers, and there's nothing wrong with defining a function that depends on these complex numbers. So this upsilon is a function of complex numbers. You don't have to think even that they are spinors. They could be any complex numbers to understand the meaning of this function. Now, what happens when we apply a transformation, of course, the one that we discussed before? The transformation of this function is due to the fact that spinors, which are arguments of these functions, do transform according to the previous slide. So when we use the form of the infinitesimal transformation of the spinors, we can find that...
Where are the values of these functions?
The value is complex valued function. Just normal complex valued function, real. Here? No, this is the... Here? No, wait. Don't read this before I start talking about this. So here, if we use the form of delta that is valid for spinors, we can find what is the form of the generator acting on upsilon. To find out the transformation of this function, we simply have to differentiate with respect to spinors. These are derivatives with respect to spinors. And then we can find what is the transformation law for these functions. So here is the line that shows that if we use the simplest possible non-trivial function of the spinors, namely the spinor itself, then this generator generates the transformation of spinors from this slide. Okay? Professor Nurowski is shaking his head in the wrong direction. Okay, could I explain something? Or no? Okay, so we now go further, and we need now the generator of translations to make the full Poincaré group. And here there is a problem, because spinors, which are in my study the numbers, do not change under translation because they are just vectors that can rotate. But this is something that has to be guessed. And my guess was that that would be a good candidate. And everything else resulted from this guess concerning the translation. This, or the definition of the translation. So I claim that when one uses this form, now how come I guess this form? Because in the Schrödinger theory, the generator of translations is the Hamiltonian, which for the free particle is quadratic in momenta. Now, since derivative with respect to a spinor is like the momentum, therefore the educated guess was that a quadratic form here would be a good candidate. Well, considering the structure of these spin tensors, that looks like a good candidate because all indices A dot and B are saturated, therefore there is only one index free, mu. So this is a good vector if you transform the spinors according to the rules valid for spinors. So we have the generator of translations. So now, when we have the generator of translations, we can do the following trick. Let's take our function, whatever it is, and translate this function. I cannot translate spinors, but I can translate functions. I just apply this operation. This is the operation that is exponentiated because I want finite translation, not just an infinitesimal translation. And that defines me a field in space-time. Suddenly, from one complex function, I have a complex field that lives in space-time. It has remarkable properties. First, it satisfies always, no matter what is upsilon, it always satisfies the wave equation, the D'Alembert equation. Second, the derivatives of this function with respect to eta and eta dot satisfy the wave equations for massless particles. Automatically, no matter what is the function upsilon. First derivative satisfies the Weyl equation. Second derivative satisfies the Maxwell equations. Without any restriction on the function upsilon, it's always true. Now, how come this is true? This will be on this slide. This is a general form of the wave equation for massless particles, and the number of these indices depends on the spin. If there is just one value, then we have the Weyl equation. For the Maxwell equation, we need two indices, and this is not yet electric and magnetic field, but you have to take some combinations which are written here. This is the connection between normal vectors of electric and magnetic field, and here is the combination of these components here that correspond to these combinations of the electric and magnetic field components. So electromagnetic field is encoded in the components of this symmetric spinor with two indices. So, to summarize this part, if you give me any complex function, and if I am able, this will be now the problem, to perform this operation, then I will get a solution of Maxwell equations.
Shouldn't be this x mu should be before p mu and p mu and after x mu?
Wait, next slide? This slide?
That's the formula in the box.
Yes.
There should be x mu, p mu, because p mu doesn't act on x mu.
No. X mu is a parameter. T, X, Y.
It is not one of x's, right?
No, this is the parameter, an arbitrary parameter or four parameters, which I will interpret, of course, as the coordinates in space-time. So here we go further, and here we are faced with the problem. The evaluation of this expression, I have written this down now explicitly, is complicated because you have to perform an infinite series of derivatives, and this is not a simple task. However, we know that derivatives become multiplicative terms when you go to Fourier transforms. So now I use the Fourier transform, but in accordance to the fact that I am using spinors, the Fourier transform is also written in terms of spinors. But this is ordinary Fourier transform in 4 dimensions, if you wish. Normal Fourier transform in 4 dimensions written in this sort of complicated way. Now, when I want to act with this object here, I can go inside the integral and replace every derivative with respect to eta. Eta are the x's and kappas are momenta, if you wish. And I get this expression, and now the problem is, what can I do with this? Can I now evaluate this integral to get a specific field now? And this, of course, depends on my choice of the Fourier transform. What is the Fourier transform that is easy to convert? Everybody knows that. It's the Gaussian. For Gaussians, one can always do explicitly, just by shifting the variables, I can perform the integration. And it turns out that Gaussians are here the most interesting examples because they produce these knotted and linked solutions of all these equations. So we came to this conclusion, and now I take the simplest possible Gaussian. What is simpler than a positive parameter A and the modulus squared of the integration variables under this Fourier transformation? So this is the simplest, and indeed one can do the integral very easily by shifting the coordinates, and one gets the following expression. What is here to be noted is this denominator. Now this denominator, a mu, I wrote this just to look nice, but of course this is just a vector that only has the time component. Now this thing here in the denominator is nothing else but the green function for the wave equation. This is what solves the, and because of this I here, it is regular. It is shifted by an imaginary unit, and that is why it's regular everywhere. Now, I have a formula. Notice where the eta is. Eta is here in the exponent, so everybody can do the differentiation. And what we get is this. You get all kinds of knotted solutions of Maxwell equations. These are the lines of the electric field. And this is taken from this paper that I have shown at the beginning of my talk. So how come we can have many of them? Because I can take, and this is what I did, I can take the sums of such solutions for various combinations. First, I can differentiate with respect to eta dot, and there will still be a solution. I can take combinations, and from such simple operations, I derive a lot of solutions of Maxwell equations explicitly given by these integrals. So now we go to the Dirac equation, which is much more complicated. Now, the Dirac equation, expressed here in terms of spinors, has this parameter m on the right-hand side, and this is what makes a difference. Before we had zeros, and that was easy. So now I have two spinors. One, this is what is like in the Dirac equation when you express it in terms of good spinors. In most textbooks, one writes the Dirac equation in a way which is convenient for physical discussions, because this is what gives in an easy way the non-relativistic limit. However, here for these relativistic considerations, it's better to use this form of Dirac equation. Actually, it goes back to Weil, Hermann Weil, in 1929, a year after Dirac has discovered his equation, wrote this in terms of spinors. And now it is natural, again, this is an educated guess, it's natural to consider this function upsilon as a function of two spinors, not just one, but because here we have two spinors. So I take this function of two spinors, and it sounds reasonable to assume that both spinors should undergo the same translation expressed by second derivatives. This is a nice symbol that was introduced due to the group of relativists in Syracuse, because they were doing all kinds of studies of relativistic systems, and they had this symbol, and Knut included this. It is called eth in the tech language. So here we have p mu, and now it seems sort of trivial. However, there is a problem with mass. The function does not satisfy the Klein-Gordon equation, because this function is used to satisfy the wave equation, but not the Klein-Gordon. In order to satisfy the Klein-Gordon equation, we must impose constraints. Not every function upsilon is good. Here, one must impose these two constraints. One says that this is m, and one says that this is annihilated by this operation. Now, this becomes sort of complicated. However, life becomes easy when you realize the constraints by writing the delta functions as Fourier transforms. The Fourier transform of the delta function takes the operator here multiplied by u and integration over u, and the same for the second. This object will automatically satisfy the constraints because this is what these delta functions are doing. So let's for a moment forget about the integration that we leave for later and ask the question, well, that sounds interesting because somehow we arrived at a six-dimensional space automatically. If you treat u and v, these parameters that were used to impose the constraints, as coordinates in six-dimensional space, 1 time and 5 space-like coordinates, then what we have is the generator of the translation in the 5th direction and the generator of translation in the 6th direction. So this operation is very much like what we previously had, except that we have now functions of 6 variables. Now, one step further. So it turns out, this is an interesting part of this project, namely, in 6 dimensions, there are nice spinors. In 4 dimensions, in 5 dimensions, they are not so nice. But in 6 dimensions, the spinors are made of 2 ordinary 4-dimensional spinors. So this fits very well with the Dirac equation where we have 2 spinors. And they form the 6-dimensional spinor. Of course, under the transformations here of the involving the 5th dimension, the upper spinors and the lower spinors mixed, because ordinary spinors are not good spinors in 6 dimensions. This is similar to what we know about parity. One spinor is not good to undergo the transformation under parity operation, but if you take both spinors, then they are interchanged. So here is the observation. This function now that is defined here, again, formally, because the problem is to do these operations. Now this function always obeys the D'Alembert equation in 6 dimensions. As it was true before in 4 dimensions, now it obeys the D'Alembert equation. Now, the derivatives of this function obey the Weil equation, which I have written here in such a form that I brought to the right-hand side the derivatives with respect to these additional variables. So this is nothing else but the Weil equation. And now notice how we recover easily the Dirac equation. Namely, if you integrate over u, misprint, where is misprint?
Delta V.
In the second equation.
On the right-hand side.
Here.
No. Here.
Oh, thank you. You- This is called Vision 2020. Okay, I didn't notice that. Of course, it should be V. Good.
This is the cut and paste.
Yes. So, let me go back and point out what should be done. We have a function of here of u and v, and we have to integrate this function over v and integrate this function after the multiplication by e to the I mu. So what happens in these equations? If I integrate over v here, and I just do integration by parts, I get 0, because I assume that this function is a regular function of v. However, before I integrate over u, I must multiply by e to the I mu. So when I integrate by parts, I get m, the mass. So this proves that everything is consistent. If I do it this way, this will be a good function because one can check by inspection that it will satisfy the Dirac equation. So we seek now the Gaussian solutions. That again is quite simple, except that there are many indices, and one should be careful not to make trivial mistakes like the one I did before. We have two spinors now as integration variables. So our Gaussian function will have this form as before, plus the part that comes from the second spinor. Now again, this is a trivial exercise in doing Gaussian integrals. I have to shift the origin, and I get this. This is the simplest solution, the Gaussian solution. What is presented here, this is taken from our paper on the Dirac equation. This is the line of the current. When you solve the Dirac equation, you can find the current. And this current here does this tricky picture. By the way, artificial intelligence liked this picture because I found this picture in the collection of pictures selected by Google in connection with these options. So they always give, they have a special case of images. You can click on images, and then this is one of the images that, of course, they don't do it by hand, but artificial intelligence probably selected this. So this is the end of my story, and I hope that I will hear some questions.
Okay. Questions, comments?
So these pictures are in this space of X's, right? In the
This picture, of course.
but of special. So it is special.
For this special solution, I write down the wave function that satisfies the Dirac equation.
Right.
And then I produce the current, psi, bar, gamma, mu, psi. And this current lives in space-time. So I can plot now the current lines and see what they look like.
In R3,
Of course,
special.
this is at fixed t.
Okay. And another thing. So since there is this u and v naturally appearing, and you interpret x as coordinates of the space-time, can't you interpret this u and v as coordinates of circle bundle over which is just bundle of null directions?
No.
So this sixth space, what is this? Can you have physical interpretation of
This
this sixth space?
is now all in what I said previously. All these nonsense about 6 dimensions was only a trick to write down explicitly interesting solutions of all kinds of equations. Forget about. I am not trying to. Okay. You are welcome, and I would be very happy if you somehow explain why 6 dimensions come in. Yes, I agree, but I don't know. Because all I know, look how I came to this conclusion that 6 dimensions are important. I just replaced delta functions by an integral. So that was a purely mechanical source of these 6 dimensions, but then it turned out that there is some physics in it, because the Weyl equation in 6 dimensions is a well-defined concept. You take spin 1/2 in 6 dimensions and see what is the relativistic equation, and this all agrees with what it should be like. So
I'm saying that there is a natural 6-dimensional space associated with space-time, which is just a bundle of null directions over space-time. So at least numbers.
Yeah, I would be, Panie Pawle, I would be very happy if you put some meat into this, because as I said, it came out sort of naturally, but there was no physical background that would lead to these six-dimensional descriptions.
Okay, more questions?
Since I still have 10 minutes, I would like to share with you a problem I just got from Physical Review Letters, a paper by two Chinese who took this solution of, this is why they sent it to me. They took our solution of the Dirac equation, they wrote down the current, psi bar gamma mu psi, and then they said that here is a new way of generating electromagnetic radiation. So what they did was to put this current on the right-hand side of Maxwell equations, everybody can do that, and then they claimed that electromagnetic field will be radiating here. And of course, when I saw this, immediately I was shocked, because everybody knows that freely moving particle does not radiate. So what happened? And of course, to make it exciting, they wrote a lot that they discovered a new form of producing radiation. In addition to all kinds, Bremsstrahlung, Cherenkov, they have a new way of producing radiation. Now, in few lines, you can disprove this in a very simple way. If you have a solution of the Dirac equation, it can be decomposed into plane waves as a Fourier integral, and each plane wave is characterized by p mu. And p mu has the property that p mu squared is m squared. When you have the product of two such wave functions, psi bar and psi, you can decompose psi into plane waves, you can decompose psi bar into plane waves, and then you have product of these plane waves, which means that these waves are moving with the wave vector p mu 1 plus p mu 2. Now p mu 1 and p mu 2 squared gives you a positive number. You can never get zero. Therefore, you can freely calculate the electromagnetic field, but this is not a radiation field, but this is some field which has no radiation component, because the condition for the current to produce radiation is that it contains contribution from the wave vector, now wave vector, because radiation field is nothing else but the difference between outgoing and incoming, and the difference satisfies the free equation. And this is how easily one can disprove this Chinese invention. Thank you.